Lionel Tarassenko from Oxford University. He was born in Paris but educated at Oxford and has spent most of his academic career in Oxford, where he is now Professor of Electrical Engineering. He's done a lot of work on medical engineering particularly, and he's won a number of prizes, and he has founded 3 university spin-out companies. In addition to all of that, he is chairman of the Oxford Pastorate, which has a mission to serve postgraduate students, and he's a lay canon of Christ Church Cathedral. Now, I'm particularly interested in this topic because I acquired a smartphone recently, and you can do all kinds of things with it, including playing chess. I believe you can also make phone calls with it, but that's something I still have to learn. So I really am looking forward to this talk very much. Thank you.
Well, thank you very much, Rodney, for inviting me. I am the outlier in many ways. Outlier is a word we use quite often in engineering, in pattern recognition, probably in neuroscience as well. No, I'm quite outside the normal envelope on at least 2 counts. I think I'm the only engineer here, possibly. I looked through the list of people. I couldn't work out anybody from an engineering school in Europe or an university part of engineering in UK or US. And I'm from Oxford. But let me just give you a very brief background, because you don't know me. I was an undergraduate at Keble College, a great Anglican college in Oxford. That's actually the view from my department, main department of engineering science, in the city of Oxford, from the 8th floor looking down to Keble College. Great college to be an undergraduate at. I could still be in bed at 5 to 9 and make a 9 o'clock lecture, which happened on a few occasions. So while I was there, it was still a college where the head of the college had to be in Anglican Holy Orders, and it was Reverend Professor Dennis Nynam, very famous for writing The Myth of God Incarnate in 1970. So we had interesting conversations with him, at least the Christian Union hymn. I then left to work for a big UK electronics company that no longer exists, called Raycall. But while I was there, we spun out a company called Vodafone, and you may still be using Vodafone for your smartphone's network at the moment. I came back to university to do a doctorate in medical electronics. I then couldn't work out whether I should stay in university or go back to industry, so I had a foot in both camps. Eventually plumped for academia, Bill, not against, and became university lecturer. And in Oxford, if you're a university lecturer, you also have to be a tutorial fellow, unlike Cambridge. And my college was St Hugh's, probably equivalent to St Edmunds in terms of endowment, and I was a very poor college in Oxford, which I was for 10 years, and then I was appointed or elected to the chair of electrical engineering 15 years ago. And now I run on the medical campus the Institute of Biomedical Engineering. So I'm a very practical engineer, and that's why I think the insights that I will offer will probably be different to the ones that have been offered by others. The sort of thing I did when I was what you call an assistant or associate professor, before becoming a full professor from 88 to 97, was designing VLSI circuits, literally tens, and by the time we finish, hundreds of millions of transistors, and we use those in various applications, but mostly autonomous mobile robots. If you think of Mars rover, for example, path planning around obstacles, localizing, finding out where you are in the world, etc., and all examples of artificial intelligence questions. But I won't actually go into that today because I've got to try and keep to the hour. What I've been working on for the last 10 years or so is pattern recognition using machine learning techniques, and I shall have something to say about that, with most of the applications concerned with the monitoring of safety critical systems. And they can either be jet engines. I've worked for 15 years with Rolls-Royce. So if you flew here on the Airbus A380, which is powered not by the Trent 500 but the Trent 900, you would have been monitored by an engine health monitoring system designed in my lab. Likewise, those of you from the US, when the Boeing Dreamliner comes into service later on this year, it'll be powered by the Trent 1000, and we also designed the engine health monitoring unit, or at least part of it, for Rolls-Royce. So not the catastrophic failure detection, but early warning signs, departures from models of normality. And now, in the last 3 or 4 years, having moved onto the medical campus and running this institute of 240 people now on the medical campus, I'm concerned completely with medical applications, and I apologise, I have to go back tomorrow to share some interview boards, so I'll have to leave either late tonight or early tomorrow morning. But the two types of activities which my research group is concerned with is either in-hospital patient monitoring, integrating the information such as vital signs, respiratory rate, heart rates, blood pressure, temperature, and oxygen levels, again to detect any early warnings of patient deterioration in levels below critical care, and then using the same thing but with smartphone technology to help people, help keep people out of hospital, people with diabetes or asthma or COPD, which is really smoker's disease, or high blood pressure, etc. So either try to detect early warnings of deterioration when in hospital, or trying to help self-manage their health using some software apps on their smartphones to try and make sure that they're able to be on top of their condition, not deteriorate and have to go into hospital. So that's really where I'm coming from. This is my one slide on philosophy and engineering, and because I'm in Cambridge, of course I have to pick probably the most or second most famous Cambridge philosopher after Bertrand Russell, Ludwig Wittgenstein, the end sentence of the Tractatus, originally published in German 1921, but in English translation 1922, and that bullet point is probably my version of what I should say about philosophy. I was well aware this morning that there are lots of philosophers and theologians in the audience. I have to declare very early on that if I get asked those questions, I won't be able to answer them as a philosopher. I may be able to give insights. For example, I've thought long and hard about the problem of free will from the very personal perspective, which I just want to share with you at the beginning of the talk, in that in November we'll be celebrating the 25 years of a major disaster in this country, which was the King's Cross fire, where you may remember 31 people died in an underground fire in London, and my younger brother was one of the victims, and I had to go and identify his body because my parents were abroad, and that forces you to think, even if you've been brought up as a Christian, about the problem of free will. Several million people use the London Underground every day. 31 were in that location when the fireball occurred and lost their lives. So I may be able to offer insight as somebody who's thought about these questions, but I'm not a philosopher, which is something I wanted to declare right up front. So what you will get today is probably quite different from the other lectures, is certain insights from engineering which are gleaned mostly from working on what we call real-world problems, real-world applications of artificial intelligence. There are plenty of toy problems. For example, the exclusive OR problem sort of kept the neural network community busy for about a decade. I would call that a toy problem, because you can realize an exclusive OR gate with 2 or 3 NAND gates, well, 2 NAND gates and an inverter. So those are toy problems. I'm more concerned about trying to use artificial intelligence to solve real-world problems. Here's an example of our high-dependency unit software, where we have hard outcomes to measure. Does the introduction of this artificial intelligence system make a difference to the number of unexpected death, unplanned admission to intensive care, or unexpected cardiac arrest? So we have some very hard outcomes to measure to see whether our artificial intelligence application is really making a difference to the state of the art. And that's the kind of very practical perspective I shall be coming from. And so here's briefly what my talk is going to be about. I'll mention the Turing test briefly, because if it hasn't been mentioned, it needs to be mentioned. Say something about expert systems, then concentrate really on my area of knowledge, which are machines capable of learning. Say a little bit about automated speech recognition and face recognition, and I hope you'll see a particular pattern emerge, which will be underlined in the conclusion. And I agree entirely. I missed the first talk, but I had a quick look at the slides, and I heard what Bill was said. Artificial consciousness is an extremely hard problem, and that's why I put a question mark. I don't pretend that I have any answers. However, it's very interesting that it is something that has even interfaced with the electronic engineering community, and it's actually quite interesting why electronic engineers start thinking about artificially conscious machines. So I shall take it from that perspective, debunk one or two myths, I hope, and then I will, and Bill has already mentioned Dennis Noble this morning, and he will feature again. He's a very good friend of mine in Oxford. I'll tell you how we got together, and I will draw one or two conclusions from what he says. And then I'll have probably one or two slides on the Christian perspective and try and draw some conclusions. So, the Turing test. Lots of programs in the UK, for those of you who are outside the UK this year, about Alan Turing, for various reasons, but mostly would it be I can't remember which anniversary we were celebrating after all that, but anyway, there've been lots of programs celebrating some anniversary to do with Alan Turing. Somebody will remind me which one it is. In any case, he was a multi-talented man. This is him on his way with members of athletics club going off to run a marathon. In the late 40s, he could run the marathon under 2 hours 30 minutes, which is pretty impressive. So he was a very talented young man who'd worked on the Enigma code breaking at Bletchley Park, interesting place halfway between Oxford and Cambridge. And in 1950, actually in Mind, which is really a philosophical journal, he published his paper on computing machinery and intelligence. Here's a sentence from it. A machine may be deemed to be intelligent if it can act in such a manner that a human cannot distinguish the machine from another human merely by asking questions via a mechanical link. Now, if you go back to the original papers, there are several versions. He was trying to think about the imitation game, where you're trying to guess whether it's a man or a woman behind the wall, a kind of parlor game, etc. I don't really want to go to the detail because I'm not really sure that it helps. I just want to recast it, what is now known as the standard Turing test. When I used to give this talk to sixth formers, when my kids were sixth formers, or the others, that was about 7 or 8 years ago, I used to talk about MSN Messenger, but like a lot of stuff in this area, that's very passé now. Nobody knows what MSN Messenger is if I mention it. But it's like if you were a human observer engaging in a natural language dialogue with two artifacts, A and B, one of whom could be a human being and one of whom could be a machine. And if you, as the human observer, what Turing called the judge, cannot tell whether one or both are human beings, and similarly for the machine, then if you cannot distinguish A and B from the dialogue you're having with A and B, then the machine, if it is one of the two behind the wall, can be deemed to have passed the Turing test. That's probably the simplest, more standard version of it. And that's really what kicked off artificial intelligence as a research topic in the 1950s. Now, what we have to be aware of course, is that's a philosophical question. It's what we call almost a software question. The previous slide we saw, we talk about messaging people via computers and so on, MSN Messenger, Facebook, emails nowadays. Of course, none of these existed at the time that Turing wrote the paper, and a lot of the forward momentum for artificial intelligence has often been to do with the hardware as much as the thinking that's gone on behind it. Because after Shockley's invention of the transistor, Bell Labs in 1948, we started really in the 60s having digital computers. Up until then, I'm old enough as an undergraduate to have done first year engineering labs on analog computers, but digital computers in the 60s and 70s became the dominating machines, and because one could program them in particular ways, those programs could duplicate decision-making capabilities of human experts, and the field of rule-based expert systems really flowered in the 70s. And that's probably the first instantiation of real-world artificial intelligence system. So I hope you can see this. Typical rule-based expert system. The key aspect of it, right in the middle, is the inference engine, which is used to reason from a knowledge base which should have been previously acquired from human experts, and that of itself is quite an area. How do we do knowledge acquisition from interacting with human experts, and then you have some data which is specific to the problem you're trying to solve. The expert knowledge is typically captured in the form of these if-then rules. If the pressure is below, I don't know, 950 millibars and it has rain today, so if and as a clause, then it will rain tomorrow. Is the kind of rules that you could have. Obviously works pretty well in this country. And so that's the knowledge base captured from talking to meteorologists in this case, whereby they transfer their knowledge about the problem into a set of rules. One of the interesting things about the expert system is they usually have an explanation subsystem, so when it actually comes to a decision, an inference, it is able to tell you which rules it has used and therefore explain why it actually had arrived at that particular decision. In other words, explain its reasoning to the user. I don't want to spend too long talking about expert systems, partly because I'm not very much of an expert in them. I've never written a Prolog or Lisp. And I just wanted to pick one particular example of an expert system, which is probably the most successful example. It's now on our phones. There are apps. I defy anybody to beat their smartphone at chess, or if they can, either they're a grandmaster or they've got the wrong app downloaded from the iTunes store. Because nowadays most smartphone apps that allow you to play chess are better than 99.99% of human beings. And even 97, 15 years ago now, an IBM computer, I'm sure most of you knew this, beat the reigning world champion at chess under normal chess tournament conditions. But the interesting thing, and this will be a recurring theme in what I say, is that actually the approach taken by the IBM programmers when they programmed Deep Blue was one of brute force. It was possible in 97 because the progress in silicon, number of transistors per millimeter squared of silicon, plus the number of parallel processors you could run together, it allowed the IBM machine to evaluate 200 million positions per second, and then to do some tree searches. You have what's called combinatorial explosion, because you can look 2 moves ahead, and the depth increases. If you look 3 moves ahead, it increases further, etc. By the time you go to 6 to 8 moves, there are a very large number of moves you have to review, and in fact, the software is able to go up to 20 moves occasionally. There were some pruning rules to abandon some searches when it was quite obvious that you were getting into a worse and worse position. Worse and worse position is evaluated by the evaluation function, which answers questions. If I've got a pawn on the right hand side of the board and a castle in between and my king is here, is that a good thing or a bad thing? So they ranked the board positions and did this again in a very brute force kind of approach, by analyzing, or by getting the machine to analyze, literally thousands and thousands of master games, and depending on the eventual outcomes of those games, to score that particular position and hold it within the evaluation function. So if you were doing search ahead with particular moves, and your evaluation function told you that it was a worse and worse position for the computer, you could abort that search. But nevertheless, a depth of 6 to 8 moves is still an incredibly powerful computer, especially if you extend it to 20 moves. Now, I read what Kasparov said afterwards, and it is quite clear that human beings, when they play chess, do not do look ahead up to 20 moves. And if a world champion might be able to see 6 to 8 moves, he won't do it for every position on the board. He won't go through, if I move that pawn here and then do this and then do that. He might select a particular area of the board and look at what might happen as he or she looks ahead, but not in the exhaustive search that was carried out by Deep Blue. So machine intelligence, the way a machine plays chess, is very different from a way a human being plays chess, and yet it's now able to achieve better performance. And there's never been a rematch. It is thought to be the case that now a properly programmed computer with the kind of processing power we have nowadays should always be able to beat the best human being on the planet at chess. And yet, so this is an intelligent activity performed quite differently by the machine than the human being. The reason why I chose chess playing is actually it's probably the best example in terms of success of an expert system. There are a few medical applications, for example, diagnosis of a low back pain, but otherwise expert systems have not been as successful as originally hoped. And the research in expert systems is now really a very minor activity in some mostly Western universities. So what is the missing ingredient? Well, round about the 80s and 90s, the whole idea of learning came to be revisited both from neuroscience. I'm sure that Bill knows Christoph Koch on the West Coast, originally German, but moved to the US around about then in the 80s. And in fact, one of the people that worked with Francis Crick and has looked at the issue of consciousness, but before consciousness was thinking about learning and saying that one of the things which is not captured at all in the Turing test is having some kind of rudimentary learning ability as part of machine intelligence. So we now have a subject which is well established, has been well established probably for 2 decades, and that's the subject of machine learning. And it's a subject that grew in parallel with expert systems, was mostly thought to be an inferior subject with respect to rule-based expert systems, but as rule-based expert system died down, this subject has really picked up. And most people who use artificial intelligence in their software probably do these days run a form of machine learning. I'm only going to concentrate on the first one, supervised learning, where you have a training data set of examples, and for each of the examples in your data set, in the training data set, you know the answer. So I'm going to take a very simple example. I'm going to imagine that we have a camera pointing at objects in the real world, and they're quite different objects to make the example easy. A car, a plane, and a boat. And so you would have examples correctly labeled of hundreds of boats, hundreds of cars, and hundreds of planes. That's supervised learning because the examples are labeled, in this case, with the class to which it belongs. In unsupervised learning, you'd have all these data set, so you'd have thousands of examples of each of the different classes, but you do not have the labels. Now, of course, if you start extracting relevant features, such as the shape, perhaps the texture, some geometrical relationships between different points on the object, etc., and use those features on their own, you probably will end up with 3 different groupings, with perhaps some overlap at the edges, so the groupings will be called clusters. So that's unsupervised learning, where you're trying to discover the groupings, the clusterings that may exist in your data set with no a priori knowledge of class labels. But I'm not going to talk about unsupervised learning today. I shall stick to supervised learning. So I'm not going to have too much mathematics in this talk. I'm sure you'll be glad to learn. But what you're trying to do is to say, take the inputs x, which, as I say, may be features describing the object, and it's in bold because there may be several features, so there will be a feature vector, and you transform these inputs through a function f to arrive at y, which is the class. So you'd have y1, y2, y3, if it's a 3-class problem, and you would learn the mapping such that if you had, say, 3 output units, the outputs be 1, 0, 0 for class 1, 0, 1, 0 for class 2, 0, 0, 1 for class 3, and you would learn the mapping f based on the input data that would generate those correct labels 1, 0, 0, 0, 1, 0, and 0, 0, 1 for each of the classes of examples you had shown to the neural network. And then the performance is evaluated on an independent test set consisting of previously unseen examples of boats, cars, and aeroplanes. Now, I have put neural networks here, although machine learning, as you'll see, is much broader than just neural networks. But neural networks were the first example, first instantiation of this type of supervised machine learning, as they can be trained using examples from a representative data set. And that started, as I say, roughly the same time as Alan Turing was beginning to think about the Turing test in the context of computing machinery. McCulloch and Pitts were doing similar things, but looking at real neurons. So they published a paper in 1943 in the Bulletin of Mathematical Biophysics, and it's still a logical calculus of the ideas immanent in nervous activity, inspired by models of the brain. So we heard from Bill this morning about long-term potentiation, which is synaptic plasticity. So modifying synaptic weights, the strength between two different neurons, which can either be positive if the presynaptic is exciting the postsynaptic neuron, or negative and inhibitory if the presynaptic neuron is inhibiting the postsynaptic neuron. So you have a very simplified, and this is the important point to stress, even at this stage, is that the model of the real neuron there is a simplified one, and by simplifying the model, we may be able to start designing artificial neurons. And as most of us here know, it was mentioned in Bill's talk today, is a neuron, if sufficiently excited, will generate an action potential, which will then travel down the axon to all the neurons of the order of 1,000 or so, maybe, to which that particular neuron is connected. So modeling of that in an artificial neuron would be taking the sum of the weighted inputs, and in their original papers, the inputs were all binary, and the synapses were also binary. This was something that was removed in the following decade, but in the original McCulloch and Pitts neuron, the synaptic weights themselves were binary. So the sum of the weighted inputs, so that's the inputs from the presynaptic neurons multiplied by the synaptic weights, which can be positive or negative, is summed. And if, for example, if the sum is greater than the threshold, for the sake of argument, let's make the threshold 0. If the sum is greater than 0, then the neuron will fire. If the sum is less than 0, the neuron will not fire. And that's the modeling of the generation of an action potential. And really, progress was not really made until the 50s by Frank Rosenblatt, who turned this into the perceptron. So very similar. So you've got inputs x1 to xn, so n presynaptic neurons, n synaptic weights. There's a bias to be able to shift the threshold. You have the summation node. So again, you're doing a weighted sum of the neural inputs. That's called A, the activation. So this linear activation, which is the linear sum of the weights times the values of the input activities. So this is the output activities from presynaptic neurons. That linear sum is computed and then is thresholded. And if you put the threshold at x equals 0, then you can generate a +1 if a is greater than 0, and a -1 if a is less or equal to 0. So the main contribution of Rosenblatt, when he first came out with this in 1957, was to make the synaptic weights real value, not just binary, and to produce a learning rule to modify them such that his perceptron learned to do simple classification tasks. And here is the perceptron learning rule, which is actually pretty, it's actually not difficult mathematics. There'll be, I apologize for those who haven't done mathematics since high school. There will be a slightly more complex equation, but not for us to go through the equation, just to understand what the equation is saying, because it encompasses a property which is actually reasonably easy to understand. Mathematical framework is just an easy way to express it. So you change a weight from an input unit I to a neuron J by a certain amount. Basically, you're going to try and change that weight to make sure that next time that the neuron sees that pattern, it generates the correct answer. In other words, if there's a large difference between what it generates and the target, what it ought to have generated, a large error, you'll make a large change to the weight, And if this is an important input, so if the input has a large value, you'll make it even bigger. So large inputs that generate wrong answers by quite a large amount, we must change that weight because that's generating the wrong output. And we do that controlling the learning rate eta. And the point is, you mustn't go all the way, because that's just that one example and that one output. You've got another 1,000 examples to show where you might want to move the weights the other way. So you make small changes and you go through random order of presentation of patterns, and eventually these weights settle down and actually solve the problem, classify the objects into 1, 2 or 3 or however many classes you need to classify them on, if they can be classified using this simple algorithm. So it's a form of error feedback. It's synaptic plasticity, as Bill was explaining it this morning, which goes on in our brains. So the memories that were being laid down, and you never know, you might remember eaters tomorrow, and weight adaptation rules such as the perceptron learning rule, because your synapses are being modified in response to the inputs to the visual cortex from this PowerPoint slide. Again, the hardware doesn't matter too much, but there's a picture of Rosenblatt actually built this perceptron and gave some demonstrations that really impressed people. It was actually image recognition that he was doing. Sadly, he died at the age of 43 in a boating accident. But I said in the previous slide that he would learn to classify the patterns if he could classify them. And this is a very simple two-dimensional example. If I want to learn how to distinguish blue dots from red dots on the left-hand side, I can solve that with a perceptron learning rule. So if I gave the coordinates of all the blue dots and then the coordinates of all the red dots in random order, I would learn the line in 2 dimensions, the plane in 3 dimensions, the hyperplane in even higher dimensions that separates these 2 classes. That's called linear separability, and it can be shown mathematically that a perceptron learns to do this and can be shown to converge to a solution regardless of the choice of the initial weights. On the right-hand side, you've got what is sometimes called the exclusive OR problem, but I won't go into the details of that. The way the blue and red dots are distributed, you cannot separate them in 2 classes with just one line. You have to have more complex decision boundaries, it's called. And this is a form of the exclusive OR problem, and it's what is very interesting because I think the general public often has this idea that we as scientists are totally pure in the way we do our science and so on. The person that really put a stop to neural network research for about a decade, it should remain nameless, some of you may know who it is, I won't mention his name, but wrote a book to show that there was a fundamental objection that the perceptron could not solve problems such as the one on the right-hand side, and therefore all the funding from DARPA, from NSF and so on, stopped for about a decade because this person was actually very keen on developing expert systems. It led to some very angry scenes between the proponents of the perceptron, Rosenblatt, Widrow, Hoff and others, and this particular person, because they felt that the monograph had been written with a view to trying to point the limitations of the neural network, in this case perceptron approach, in order to promote, with a hidden agenda of promoting the alternative approach of expert systems, because in the 60s it was neck and neck, touch and go between the 2 different forms of artificial intelligence. So that probably tells you something more about human beings than science, but nevertheless, there's influences. I'm sure those of us who are scientists have come across them in small or large doses. Actually, it's fairly simple to solve the problem. You can almost see it graphically. If I could take a linear classifier that generated a straight line this way, another one that generated a straight line here, and somehow was able to combine their outputs together, then I could probably solve the problem. And that's exactly what the multi-layer perceptron does. It combines the outputs of a number of perceptrons with the inputs here, so this is a number of single layer perceptrons here, and then the outputs are fed to another layer, and so it becomes a multi-layer, what's known as multi-layer perceptron. And actually that was probably known at the time that Rosenblatt, Widrow, Hoff and others were doing battle with the proponents of expert systems. The big problem is, remember the learning rule was about synaptic plasticity? How do I change the weight so that next time that pattern is being shown, the network, the perceptron is more likely to give the right answer? The error feedback procedure is a bit difficult. I show a pattern here and I get the wrong answer here. So instead of getting 0, 1, 0, I'm getting something which is closer to 1, 0, 0. So I'm going to have to adjust the weights to these two units so that next time I show that same pattern, they're more likely to give the right answer. So you have what's called the credit assignment problem. Because now, how do you assign the blame for getting it wrong to these weights here, from what I call the hidden to output units, with respect to these weights here? And actually, it's simple mathematics that gives us the answer. It's done using the chain rule, provided that you replace your hard limiting function, if you remember, above threshold generator +1, below threshold generator -1, that's called hard limiting, or the Heaviside function, by a continuous differentiable function. So a soft version of this hard limiter, which is called a sigmoid function, which is sort of shown here. It's not very well shown, but it's sort of, instead of being a hard limiting here, it has a gentle slope around the hard limiting. We can write the equation for that, this function f, and we can differentiate it f dash. So I put the equation so that just in case there were people here who knew the mathematics, they could check that I've done so correctly. I'm not going to take you through it. All it shows that simple kind of last year of high school mathematics, provided instead of having a hard limiting function, which is an infinite change from -1 to +1, as you go from just below 0 to just above 0, to a smooth change from -1 to +1, what we call a sigmoid, and provided we can differentiate that function as we can, then we can solve the credit assignment problem. In other words, how to adjust the weights in the two different layers of this multi-layer perceptron. And that led to an explosion in the 1980s. It'd be interesting to hear Bill's perspective of how that affected neuroscience in his patch, where he was a neuroscientist. But certainly the parallel distributed processing architectures of Rumenhart, McClellan and Hinton from the West Coast and so on had a huge influence in Europe and in the US as well. As soon as we learned how to use these multi-layer perceptrons to solve hard classification problems. He wrote a book in the late 90s about how to do this on a real-world application, one of which is shown here. This was the most successful microwave oven in the mid-1990s in the UK. What we had done, I can tell you at dinner how this all came about, it was quite interesting, is actually we learned the patterns of humidity with a humidity sensor inside a microwave oven, as you put either a cup of coffee or some food you wanted to reheat from the local supermarket. The Japanese coined this wonderful word called doneness, the doneness of the food, and we learned various shape parameters of the humidity signature to predict the doneness of the food at that particular time. And this worked so successfully, just put your cup of coffee or the chicken tikka from Marks and Spencer in the oven, press the button, and it was always done perfectly. And this literally sold hundreds of thousands in the UK until the project was aborted because the company felt it was paying too many royalties to the University of Oxford. But that's another story. So that is probably one of the first, if not the first, example of using a neural network to solve a real-world task that was used by hundreds of thousands of people in their kitchens in Europe.
Do you have any now that will get the food warm in the middle?
That's easy to do. Actually, you have to remember to put it eccentric on the plate. The problem, still too many microwave ovens, you can't put the food, you put it in the middle. And of course, if you study the patterns of radiation, there are hot spots and cold spots, depending on geometry of the object, the thermal conductivity of the chicken, or whatever, and therefore it's not warm. What you have to do is to buy a microwave oven which has a rotating plate and make sure it's eccentric and therefore travels through both the hot spots and cold spots. Amazing what you learn on these courses, isn't it? of the cavity of the microwave oven. So just to show you, this is actually something we also confront from time to time as scientists. It's very difficult. This, I completely disagree with the marketing literature that Sharp used, but by the time it had left my lab and become one of their projects, I had no control over marketing literature. And so this, I would really put a red cross through that, but it is actually how it was marketed by Sharp in this country. And again, I think it's something that we as scientists have to think long and hard about, is how the fruits of our research are exploited and where are the boundaries of what we can actually control and what we can't control. That's another ethical discussion. Right. Trying to finish the next 20 minutes, let me speed up a little bit. Now the interesting thing, however, we started in 1943 with McCulloch and Pitt's neuron. We got to the perceptron in 1957. There was still some biological plausibility. Bill would have been able to, as a neuroscientist, been able to recognize the neurons. By the time you go to the multi-layer perceptron, there is no biological plausibility. There are still some people in the psychology literature, I hope not in the neuroscience literature, who are using these as models of biology. They are not biologically plausible. The multi-layer feed-forward architecture is not biologically plausible. The resolution you need at least 16 bits, so 1 part in 63,000 precision in order to change the weights when you do these weight updates to make sure that you get the correct answer next time round, is way above the kind of precision that real neurons of the order of 1% are the synaptic adjustments. So there's no biological plausibility left at all in a multi-layer perceptron. And although it was originally modeled on biology, this form of machine learning is very different from human learning. You may see where I'm going now. It's becoming slightly, perhaps, obvious, I hope. One final comment. We've moved on from multi-layer perceptrons. I'm going very quick through this. Machine learning, actually, multi-layer perceptrons were very helpful in getting us there. Is a form of probabilistic pattern recognition. Instead of having the code 1, 0, 0, 0, 1, 0, 0, 0, 1 to identify boat, car, and plane, I can actually turn that to probabilities. So when I show the camera picture, one output may have a value of 0.7, so probability it's a boat of 0.7, probability of 0.2 it's a car, and probability of 0.1 it's a plane. So they have to sum to 1, of course, so we can turn the outputs into probabilities. And so the task is to estimate the probability of the output given the input feature vector and the parameters of the model. And in what I've just shown you, in a multi-layer perceptron, you learn using this error feedback, the function f, you learn to estimate it. You can actually turn the problem around. This was shown in the late 1990s in what's called a generative approach. Instead of doing py given x, you do probability of x given y. So what are the distributions of feature vectors for each of the types of classes you have? You have a prior probability also of these classes over the different models that you have. You use Bayes' rule. And the Bayesian approach, you're saying, in fact, one model, one multi-layer perceptron with these weights, actually that's a pretty poor solution. Really, there's probably large numbers of models out there, and we can integrate over all possible models. And you end up with what's called Bayesian machine learning, and that is the state of the art. It's actually only this one slide, really, from where we were multi-layer perceptrons 15 years ago to where we are today with Bayesian machine learning. But it takes us even further away from all biological plausibility. So let me talk for about 5 minutes about applications, and leave myself 10 minutes for consciousness. So I worked when I was at Raycor and Vodafone on automatic speech recognition, and we started with what's called the channel vocoder, where we took the input speech and we looked at the energy in various bands from about 200 hertz to, this was a telephone quality, so 3.2 kilohertz. And we modeled that on the human cochlea. And if you look, one particular aspect that is similar to the way the human cochlea works is that the bandwidth of the first filter is 200 to 300 to 100 hertz, and here 2.8 to 3.2 kilohertz, it's 400 hertz. And we know the cochlea works exactly the same way. As you go up in frequency, the passband of each bandpass filter expands. So this is ideas drawn from our understanding of the human auditory system in order to design the very first automatic speech recognition system. So that's about 25 years ago. If I look at a paper of the last 4 years, this is the conclusion. There's so far little or no evidence that the study of the human auditory system has contributed to real significant advances in automatic speech recognition. So today's speech recognizers do not use any biological plausibility as part of the way that they're configured. I was going to spend a bit of time on that, I'm not, and you'll be glad to hear. This is actually a hidden Markov model type of speech recognizer, where you've got an acoustic model, lexical models, language models, much more complex than a simple model of the human copier. And indeed, the person who wrote the paper for Dragon Systems here was a company that spun out of the government communication headquarters in Cheltenham. There's plenty of software there for $60 or less that allows you to do automated speech recognition pretty successfully, 97-98% recognition once trained. And I'm not going to say any more because the real experts in this country in this domain are just down the road in Trumpington Street in the Cambridge University Engineering Department. So adopting the Wittgenstein approach again, I should let the Cambridge people talk about this rather than me, but they're now at a stage where they can do not just English but Arabic with recognition rates in the upper 90s percentage-wise. Other application of probabilistic pattern recognition is face recognition. It's quite difficult to do, even if you have the same camera angle. I'm not even going to look at the problem that neuroscientists look at, because that would be another half hour of different viewing angles. Even for the simple task of a face, more or less face on, plus or minus 10 degrees, if you vary the contrast and the amount of light on the scene, it actually is quite a difficult task. Bill may be aware of this work. Somebody about 10, 11 years ago, Delorme and Thorpe, tried to build a face recognition system using biological plausibility. So Bill should really talk you through the top of this slide. On-center and off-center units. So you have units that recognize black circles within the white, or white circles within the black circle. That's the way we believe the retina works. And then you have orientation detection. You can see those rotating through 45 degrees. And so you show an image, and these fire. If you have 40 faces to recognize, you have a sort of what is called a winner-take-all network. So when you have the firings here from the neurons associated with phase 3, you strengthen those connections, high excitation, and inhibit the connections to all the other faces. And like that, you can learn what I call spatially organized neural maps, and you have visual information propagating, again, in feed-forward fashion from retina to visual cortex to higher levels of cognitive processing. However, although this is reasonably successful, it's nowhere near as successful as the machine learning systems which have no biological plausibility, and in fact, it's a software simulation, and again, it misses really the ability to have the complexity of the visual processing systems such as a real neuroscientist would want to see. And so most facial recognition algorithms work quite differently. They do landmark recognition, relative position, size, shape of eyes, nose, cheekbones, etc. And then you do very large searches to identify faces that you have previously stored in your memory. Rodney, you've probably got one of those on your phone if you want to. You can go to the iTunes store and download one, and it'll help you to identify the faces of people on Facebook if you want. Although there's some controversy now about whether this infringes privacy laws or not, and there's some interesting blogs going on at the moment in cyberspace. I just mentioned one application locally, which is an application which we have sold to Hollywood from our Department of Engineering Science in Oxford. It's actually identifying various actors in videos. So it's a system designed by my colleague Andrew Zisserman, who's won the Mar Prize 3 times, the only person to won the Mar Prize 3 times, one of the most important psychophysics prizes in the visual world. I'm not going to go through all of this, but it's a combination of machine learning. Kernel-based regression is machine learning working on the raw pixels to identify faces and new faces when they pop up in the image. Then you have a pictorial model using the sort of facial features I showed you before. And then you have a form of classifier, which is a tree classifier with probability estimates of each node called random ferns. There are random ferns, random tree classifiers. And you marginalize according to a Bayesian approach. So there's machine learning at the front end, machine learning at the back end, with extraction of facial features. This is remarkably good. I've seen it run in real time. You can say, show me all the scenes in Mission Impossible 3 in which Tom Cruise appears, and it does it. So it's a visual Google search, which has been developed by a colleague of mine, Andrew Zisman, in our lab. So my conclusion, so that I can have 5 to 10 minutes, probably, on consciousness, is a very interesting phenomenon has happened over the last 60 years. State-of-the-art machine learning algorithms for the most common applications, speech and face recognition, actually bear no resemblance at all to the original models of human learning. So having started with trying to model how human beings learned how to recognize faces or speech, we now run algorithms on machines that are completely different to the way neuroscience tells us human beings do it. So let me just talk very briefly about artificial consciousness, not to give any answers, but to point one or two things from how it's impinged my work as an electronic engineer. So you see this appearing in electronic magazines quite often. The fact that Moore's law, etc., that I'm sure you all know about, exist. We have this huge increase every 18 months. The amount of computing power doubles, and so you can do a log graph to show. It's obviously linear, but if you use a vertical scale, logarithmic scale on the vertical axis, that we are going to nearly 1 trillion transistors within probably 20 years of now, certainly. And so there's this idea that the number of transistors keeps increasing, gets close to the number of neurons in the human brain. In a number of electronic publications, they would argue that will go from the Pentium to Brainium. And this almost sort of conclusion in the articles that as a result of that, we will actually create electronic machines that are conscious. And so I've asked myself, why is it that electronic engineers would want to draw these conclusions that, as we increase the computing power and get to similar number of processors as there are numbers of neurons in the human brain, that consciousness would appear. And so I did a bit of digging around, and in fact, what is very interesting is what Bill was talking about. It's bottom-up determinism. It has become an all-pervading influence. It actually works if you look purely in the electronic world. So I was thinking during your PowerPoint illustration of running it and whether you use the same transistors or not. That probably depends, Bill, exactly which programs you're running before and so on. So you may or may not be using the same transistors. We could get down to quite low-level electronics to discuss that. But you certainly will not be using the same electrons. So if you're worried about the analogy, don't worry about going one level below. The electrons that form the currents of those transistors would be different electrons. So it's not a point of discussion. But this is actually 2 years of our electrical engineering degree course in Oxford. We start telling them about electrons. We tell them about Heisenberg's uncertainty principle. So if you know the speed electron, you might not know exactly where it is. We know how electrons form transistor currents, how you put transistors together to get gates, which you can assemble. You get the hardware description, language, etc. High-level language, such as BASIC, C, Fortran, C#, C++. That gives you the programmable computer with all the applications I've shown you. Absolutely no problem with that. This is what I teach undergraduates in years 2 and 3. Information flows upwards from electrons to transistors. So this idea of the bottom-up determinism sort of works as a picture if you stay purely within the realm of electronics. But why is it then that people draw an extra arrow and put consciousness at the top? And really, as I say, that is because the biologists have spread their all-pervasive influence to every discipline, including electronic engineering. And I cannot think of any other reason except that it is so accepted by scientists who are not experts in biology that the reductionist bottom-up approach is really the way things are, and so they apply it to electronic engineering. And it is a very commonly held view. Why is that? Well, Bill showed a very similar slide this morning. If you go to the reductionist bottom causal chain in biology, you start the genes. If you don't go down to quantum level, information flows upwards from DNA to proteins and upwards, etc., through the higher levels. And then this is where, and it was originally came from France to Jacques Monod, who won the Nobel Prize in the 60s, but he was the first one to coin the phrase of the programme génétique, that we're all determined by what happens at the level of our genes. So bottom-up genetic determinism. But they don't stop there, and I think this is the interesting thing for our study here, perhaps this week, is that actually the Dawkins and Crick do not stop there. I'm sure this statement is well known to a lot of you. It's in Francis Crick's book, The Astonishing Hypothesis, Crick of Crick and Watson, the discoverers of the structure of DNA. As Lewis Carroll's Alice might have phrased it, you are nothing but a pack of neurons. So, how did this actually come to impinge upon my work as an electronic engineer? Well, about 6 or 7 years ago, the Royal Academy of Engineering, of which I'm a fellow, got together with the Academy of Medical Sciences and asked us to write a report on systems biology. And we're all paired off, engineers with biologists. And I was very privileged to be paired off with Dennis Noble. And I learned far more biology than I think he learned in the electronics, but that's another story. And I actually read proofs of some of his book, The Music of Life, which is actually a wonderful book. Dennis is a very interesting person. He's a polymath. He can speak Korean, he can speak Occitan, which is a language of southern France, which is more or less extinct, as well as writing this very beautiful book, which I recommend to everybody if you haven't read it yet. But the interesting thing is that, and one doesn't hear this from the Crick-Dawkins school of thought, is actually that the reductionist bottom-up view is oversimplistic. That's the view, bottom-up determinism, and Bill's arrows were going up and down here. Here there are some arrows that go around the outside because there are feedback systems, and the interesting thing is not just feedback from one level above down to the level below, it can be at all sorts of levels. Quite high levels control gene expression at a very low level. One level to the next is protein reading the genes, the protein machinery reading the genes, but at higher levels, even mechanical inputs, you can shock the heart and trigger cell changes in cell signaling and so on. So the bottom-up reductionist view is actually oversimplistic because it doesn't include feedback from the higher levels. Now that really gets an engineer interested because the whole of electronic engineering is based on feedback. It's called negative feedback. All the control systems that we design, whether it's to fly an airplane, whether it's to control a chemical plant, are all based on feedback. And the fact that systems biology, and it's no longer bottom-up or top-down, it's inside-out, as Dennis Noble and Sidney Bruner call it, you need that whole picture to understand. So there's upward as well as downward causation. And of course, I'm sure you've got this immediately, the downward causation modifies the components responsible for the upward causation, which in turn modify those generating downward causation, etc. So you have a very complex, non-linear feedback system, which is completely absent from the oversimplistic, bottom-up reductionist view propagated by Dawkins and others. So we can dismiss the electronic, so I can go back to my electronic engineering colleagues, as I often do, and tell them, okay, on the left-hand side you have electronic computers composed of billions of transistors, arranged this linear feed-forward architecture here from electrons upwards, but the multi-level feedback loops and complexity of living organisms on the right are not captured in designs of these electronic machines, and therefore increasing number of transistors such that they have the same number of neurons as in the human brain will not lead to the emergence of consciousness at the highest level, the feed-forward architecture of the electronic computer, simply on architectural grounds. In other words, that there's a huge element of nonlinear feedback missing in the operation of the conventional computer. So, what about simulation? Just very briefly, we might not be able to build it, but could we simulate it? And this is also in Dennis's book. Well, if you think about this, and I won't have time to go through in details, but on the scales of length, you go from 10 to the minus 12 in the atom to about 10 to the 1, so 13 orders of magnitude. And likewise, on the scales of time, you go to 10 to the minus 4.1 millisecond to 10 to the 9 seconds, which is a human lifetime. Even if you take something right at the middle here, the cell, and you want an accurate molecular reconstruction, the activity of a single cell, then you need to simulate the interactions around 10 to the 12 proteins. And I'm sure many of you know that actually the reconstruction, the chemical process involved in folding just a single protein require dedicated supercomputer for several weeks. And therefore, Dennis writes that there isn't enough stuff in the whole solar system to build the computers required to simulate accurately the activity of a single cell in the human body over the temporal and spatial scales required. So it's not actually possible to build an accurate simulation of a human being, even at the cellular level, even if you just wanted to do that particular cellular level. So you might ask, why is Dennis Noble the leader of the Human Physiome project? We can talk about that during the discussion time, because you then take shortcuts, which are quite interesting in themselves, but they are shortcuts. So finally, with my last 2 minutes in conclusion, I think, as I have said, and it is beautifully laid out in Dennis Noble's book, the reductionist approach ignores complexity. As soon as you have nonlinear feedback, any second or third year engineer can tell you that the mathematics of this gets extremely complex. And therefore, if you ignore the existence of nonlinear feedback loops, you will have an oversimplistic interpretation of the biological data. And Dennis goes further. So Dennis Noble is agnostic. He's not a Christian believer, but he's agnostic. And he says the bottom-up reductionist approach is not so much an interpretation of the biological data as the reflection of pre-existing assumptions about how things are meant to be generally. So bottom-up determinism using a simple feed-forward architecture is effectively saying a reflection of pre-existing assumptions, or in other words, a statement of faith. And therefore, we can say, I can extend that by saying that statements such as "you are nothing but a pack of neurons" are also nothing more than interpretation of data based on the pre-existing assumptions of Francis Crick. And so what we have to do is to challenge that community and tell them these are pre-existing assumptions. Yes, as Christians we have different sets of pre-existing assumptions. We start with the prior belief that we've been created in the image of God, who's beyond time and space, as described in Genesis chapter 1, and we are willing to acknowledge those prior beliefs, but what you find is the other side of the community, the reduction community, will not ever acknowledge the fact that they also have pre-existing assumptions, or in very few rare cases, except people like Dennis Noble. So, the beliefs that we have, for example, from our reading of Hebrews, that great chapter in Hebrews chapter 11, about faith, that we've been created in the image of God and there's an invisible world beyond the visible, accessible by faith. So this invisible world is accessible by faith, whereas the visible world is accessible by our senses and our scientific instruments. The kind of statement, like Hebrews 11 verse 3, is not a scientific statement. And what is very interesting, Dennis Noble, just after page 100 in his book, say, we cannot say everything we want in scientific language. And that was the point of what Bill showed this morning. You have on the left-hand side what Dawkins wrote about the genes, and on the right-hand side you had what Dennis Noble rewrote about the genes, but viewing genes as prisoners. And he says there is no scientific experiment that you can do to generate the empirical data to distinguish between left and right. Therefore, whether you choose whether it's left or right is not a scientific statement. It's based on pre-existing assumptions that you have about your view of the world. And so I just quote Pascal here because I went to the Blaise Pascal school when I was in my teenage. He never actually talked about the God-shaped vacuum, but he talked about an infinite abyss that could only be filled by God himself. And this is a statement of faith, but that would be my minimalist contribution to artificial consciousness. That is what I believe, as a statement of faith, distinguishes us from machines. So, finally, to conclude, just to summarize some of the points that I've made in the last 2 slides, 5 points. Definitions are needed, but of course they're difficult. Where we can contribute something as engineers, computer scientists, is that we have to have specific outcomes. So we can propose task-based definitions, such as human-machine dialogue, chess playing, speech, face recognition. There's a well-known definition from Tom Mitchell that we could all sign up to. A computer program is said to learn from experience E with respect to some class of task T and performance measure P. If its performance of tasks in T is measured by P improves with experience. So we can all sign up to what that definition of machine learning is. How we define machine consciousness, which has not been attempted in this lecture, I've just attempted to show some of the shortcomings of the simple bottom-up feed-forward structure when applied from the simple view held by reductionists and transposed to electronics. Obviously, that is a problem, but it certainly helps to focus the thoughts of electronic engineers to why actually consciousness may not just arise out of a collection of neurons in this case, when we're talking about a collection of transistors in this case, when we're talking about artificial consciousness. And finally, I think personally that we have to go on the offensive, that statements made by reductionists such as Dawkins and Crick need to be challenged. We need to say that you don't have to be a Christian believer, you can be an agnostic like Dennis Noble, to say that those are not scientific statements. Remember the left-hand page, the right-hand page that Bill talked about, these are interpretation data based on their pre-existing assumptions, not scientific statements. We have to say that loud and clear because the general public believes those statements to be scientific statements. And an interesting point that I've mentioned several times is although we started looking at things like learning, pattern recognition, in various forms of intelligent tasks in the way human beings do them, our most successful instantiations of learning in machines are completely different from the way human beings do so. Thank you very much.
Well, that's a great talk. So Dennis has a question to kick us off.
Yes, I'm curious if on these simulations of complex systems like cells, what difference would it make if there was a wonderful quantum computing available? How would that change the scenery on that topic?
Well, it depends who you talk to. If you talk to Andrew Briggs, for example, I'm sure he'll tell you all the difference. It's a Gedanken experiment at the moment, what quantum computing may or may not be able to do. The level of how far they've got, I mean, they are making progress. Having said that, the quantum computing IRC in Oxford has not been renewed in terms of its funding, so progress may be slower than the funding authorities were hoping. So I think it's several decades away being able to run general simulations on a quantum computer. They do very specific tasks with their quantum computers. They have to be set up, as I'm sure you know, in extraordinarily controlled conditions because it's often done with laser light on vibration-free table set. Doesn't mean that in 50 years' time we won't have quantum computers. In terms of the practicality of it, we're so far removed from being able to do a general-purpose simulation of quantum computer that it probably doesn't impact our generation, possibly the next generation of scientists. As a thought experiment, then of course the ability to, it's not a point that Dennis Noble addresses in his book, the ability to run all of these different possibilities in parallel would obviously speed things up. The great problem always in quantum computing is you have this massively parallel computation, all these possibilities being computed in parallel. How do you collapse the wave function to extract the single answer? And it's a problem that nobody quite knows how to do in order to do a realistic computation where you actually want an answer out of it. And so the output problem from quantum computing, as far as I understood it, is not a solved problem at the moment.
Thank you, that's helpful. David?
Same kind of spirit as the last question. Can you speculate on the potential relevance in the future possibility of the science fiction idea of incorporating living tissue into machines?
I think you should probably ask that to Bill, probably. Well, to me it's very interesting. I mean, Bill mentioned various experiments where certain aspects of the brain have been damaged or replaced, so there's absolutely no doubt that with artificial retina, artificial cochlea, this is already happening. We are able to replace certain parts of the human brain, as far as I know, mostly to do with processing of auditory or visual information. I don't know of any human enhancement done. Do you know any, Bill, that is not to do with either the auditory or the visual cortex?
Yeah, there's some really nice stuff going on in motor prosthetics right now. Putting chips into the motor cortex, reading out the intention to move, and using the chip to be able to control prosthetic and paralyzed or light and ALS patients.
So that's the human-computer interface.
Yeah, absolutely.
And all that does effectively is move the sensors within the brain, because actually if you, having done some work in there, the big problem with the human-computer interface up until now has been from the EEG, the electroencephalogram. So you're using sensors on the skull in order to read the electrical activity of the cells within the brain. Obviously, if you can move the sensors within the brain, you can have a much clearer idea. And there's absolutely no doubt that you can associate certain types of neural firings with certain actions, and so there are some very good demonstrations. There's a process of learning, and again, there is a group in our department in Oxford that does this. They actually use very complex machine learning algorithm to associate the sensor data with the correct response. So I think in all of these questions at the moment, it's all about enhancing our ability to read the appropriate sensor data, whether from the motor cortex for people who are paralyzed from the neck downwards, or from the auditory or the visual cortex. Take that information out from these sensors and process it, actually probably not like the human brain would do it, using the point I was making, but using some very powerful machine learning algorithms to generate the correct responses. That seems to be, again, the way to do it. So there's a kind of a break. Now, some people have argued, and this is why the brainium keeps coming back as a point, is that the reason we have to do that is we don't have massively parallel architectures like the brain, which is literally, 10 to the 10 neurons each with at least 1,000 synaptic connections. And if we had that kind of massively parallel architecture, then we would be able to do it with biologically plausible hardware. And it is a very big project in Switzerland funded by the European Community to do that. I still think it's a fundamental problem that in order to compute anything that we can really understand the mathematics of, you do need these simple feed-forward architectures. And we know that there are multiple, not just in going from the genes all the way up to the organism, but within the brain itself, lots of feedback circuitry. And as soon as you put feedback and it's non-linear, it's extremely difficult to analyze. And so I actually think the most promising avenue at the moment now is to use the technology to improve the sensor data and use these machine learning type algorithms, which are quite different from the way the brain processes information, to generate the response that the brain would have generated. But that's only a personal feedback.
If I may, my question was actually the other way around. That's fascinating, but I was wondering whether things like ion channels and neurons, cell membranes might be able to be incorporated at some point into machines rather than the other way around. If they can do things better than metal can.
It would be difficult to understand why you'd want to do that, because, for example, as I was showing in the multi-layer perceptron, that's the argument that I was trying. I apologize, I was trying to pack about 2 lectures into one. I hope that's not my phone. Into one, so I had to go past several points. But if you look at this learning algorithm, the precision that you need at least 16 bits precision, which is 2 to the 16, 64,000 or so. So you need to be able to change one part in 63,000. The neurons that you'd be able to extract from the human brain, as far as I know, Bill can contradict me, it's 1 part in 100 roughly the changes that you can make. So how is that really going to help you in this particular instance of synaptic modifications to have a real neuron as opposed to a one made of metal or silicon.
What do you make of the Roger Penrose argument and J.R. Lucas, the philosopher before him, that Gödel's theorem essentially shows us that algorithms, the brain doesn't, we as humans don't work algorithmically. I mean, that seems to be confirmed in some of what you're saying here, from a practical point of view. But in some sense, we can't be simulated by a digital computer.
Well, that's exactly where I wanted to go without mentioning Gödel. So thanks for, because that is beyond my own understanding. I get into the parts I don't understand. I can't say that I know enough mathematics or philosophy to understand those arguments, but it's exactly what I wanted to demonstrate in a practical engineering way, that actually, Deep Blue didn't play chess like Kasparov. It doesn't recognize your face like I'm recognizing you, having met you on your own today, our brain. Likewise, in terms of speech recognition. So we don't compute, if I can use that word, in a way that machine algorithms compute. This is simply an engineer's observation I have.
Okay. Yeah, okay.
One of the things that would concern me, you're a Christian, and within the whole Christian framework, the tendency I see that's happening is that people becoming more reliant on technology than they are upon I'd say the value systems that they should have to operate really effectively. And the thing that concerns me from what you're saying is we're getting closer to a society where machines are playing far too preponderant a role in the way we lead our lives. I'll just give you a little example. I'm having dinner with some people in Naples in Florida, and they say, well, let's take the boat down to further down the coast. And we get on board, there's no life jackets, and there's no mobile telephone. And the guy's relying entirely on his boat. And I said, but just a minute. And I think about it, fortunately the wind's coming on shore and I don't make a big deal about it. But that's the problem, is that people are no longer thinking as effectively because of technology, because they're relying on, they're putting themselves in a position where they're relying on technology, but if the technology there, I'm sorry, but they're absolutely screwed. And that's what worries me about the way the world is going in terms of technology is almost replacing spirituality. Does that concern you in what you do?
It's a question of boundaries. I think it's very important to state the problem. But to me, it's exactly the same as nuclear weapons. Nuclear weapons cannot be disinvented. Technology cannot be disinvented. So your mobile phone call, whichever person's mobile rang, or the one I'm going to make later on, say to Oxford, to my wife tonight, will be routed through multiple cells using artificial intelligence. The fuel injection system in your car has got a machine learning algorithm. It's all pervasive technology. And you cannot undo that, disinvent that. I think what you can do is to say, we need to have a reflection upon that. Where are the boundaries? For example, I will not use sat-nav. That's a personal thing. Because I like to know where I am. I like to know whether the car's pointing east. There's a place, for example, Birmingham, in the city. Who has got lost in Birmingham here? Everybody's got lost in Birmingham. Sat-nav won't help you because you go in and out of underpasses. I got out of Birmingham because I knew where the sun was and I knew which direction I wanted to go. So I was navigating like they used to do in the Middle Ages and so on. So we have to think about where the boundaries of our use of technology is. But I think that's a broader question. It as I say, goes all the way to nuclear weapons. We cannot disinvent nuclear weapons. So how do we deal with that particular form of technology? We have to think about the boundaries, and we have to say there are boundaries, and we need to decide where they ought to be.
Thank you. Yep. Question? Yep.
I think the cornerstone, which is very interesting, is the statement number 4, and the second sentence. There are nothing more than an interpretation of data based on pre-existing assumptions, not scientific statements. Can you say a bit more about what are those pre-existing assumptions are? Just to make comparison between these Dawkins and...
Well, the best example was from this morning's talk. I don't know if Bill's got his... because I have the book with me, but I don't know if we've got the slides for this morning on It's a case-based set of pre-existing assumptions. In this case, it's the case that genes are, from the bottom up, determine everything that happens at higher levels. So it flows one way, it's bottom up, and therefore you can have the reading of the left-hand page that is all about genes controlling us and determining the way we act and behave. Or on the right-hand side, what Dennis Noble calls genes are prisoners. They're there, but we are effectively controlling them. So it's a different set of assumptions. The whole page is rewritten as if genes were part of us, yes, but they are prisoners. They're not the determining factors in the way we behave or act. So it's a different set of assumptions. The point he's making about those two texts is that you can write the text on the left-hand side or the right-hand side. In fact, here's another version in the next page where he mixes the text. He says there is no scientific experiment where you could collect empirical data that would allow you to distinguish from left and right-hand side. Therefore, it's not a scientific statement. And interpretation on the right-hand side, which assumes that genes do not determine what we do or how we behave, is as equally valid from the scientific point of view as the selfish gene interpretation.
But you are saying that there are real downward causation effects and so on.
Mm-hmm.
So it's not just, it isn't. I mean, you
Absolutely.
are making
No, but
you're making what might be a scientific statement there.
Yes.
That there really are downflows of causation, it isn't all.
Yes, I mean, there are downflows of causation which can be demonstrated very easily. I mentioned the mechanical, because Dennis Noble was really the world expert on building a model of the heart. He has built models of the heart which begin at the genetic level. He has some genes that are involved in calcium channels, iron transport across ion channels, and all the way up to the whole heart. And you can run simulations, and he can show the effect of his pharmacological agents in terms of prolongation of certain intervals within the heartbeat, the QT prolongation and so on. So it's a fantastic piece of work, and you can show quite right. One of the downward causation is if you hit somebody very hard on the heart to give them a mechanical shock, then actually you can cause sudden death. The cellular activity actually stops completely, and that comes from a physical blow to the organism, to the organ in this case, that has this effect on the cellular level. So there are well-known experimental data that show that there are these feedback loops. I think the argument about left-hand page, right-hand page comes early in the book about saying that actually the selfish gene on its own, never mind forward and feedback loops, is something that is a statement that is not supported by what we call scientific evidence, the ability to run an experiment and collect empirical data to show that page A is correct with respect to page B, and then he goes on later on to explain that this simplistic view and the upward causation is a limited view because it doesn't incorporate the feedback loops. That's a separate argument to the one from the left-hand and right-hand page.
Okay, thank you.